Welcome to Sleepy Space Science. Tonight, Black Hole Seeds opens the missing beginning behind cosmic giants. Rewind a supermassive black hole and the blazing disk narrows toward one hidden ancestral seed. Every galactic giant needed a first threshold before feeding jets and influence could begin at all. Light seeds from massive first stars feel natural, yet cosmic time makes them struggle early. Between stellar ashes and giant origins, the universe leaves gaps that still demand wider possibilities. Heavy seeds promise a head start if pristine gas collapses without becoming ordinary first stars. But gas resists simplicity, spinning, cooling, fragmenting, and turning collapse into a fragile cosmic contest. Feeding black holes fight their own light as radiation presses outward against falling fuel itself. Growth therefore becomes uneven, shaped by angles, shadows, dense streams, and brief sudden openings in gas. Brief violent feasts may let small seeds gain mass faster than calmer early models predict. Mergers can combine dark beginnings, but orbits must shrink before mass can truly join together. Early galaxies were nurseries where gas stars' feedback and halos decided each seed's fate locally. To see those nurseries, observation must move from theory into faint ancient infrared light itself. Webb sharpened the puzzle, revealing early active black holes and compact red sources previously blurred. Little red dots may mark hidden accretion, unusual stars, dense galaxies, or transitional states instead. Spectra X-rays, gas motions, chemistry, and statistics must separate seed histories from bright confusion together. The old light-heavy split softens into a spectrum of beginnings, environments, and growth routes combined. Seen this way, every seed becomes a clue pointing backward through deep cosmic ancestry itself. Seeding reads the early universe itself from first stars to cleaner gas and assembling structure. No single pathway is proven. Giants may preserve many beginnings shaped by environment and time. Like, subscribe, and thank you for listening as we rewind the giant into its seed. A giant black hole is easiest to imagine at the end of its story when it has already become the dark center of a galaxy, when gas burns around it in a bright accretion disk, when gravity has gathered enough mass to bend the paths of stars and light itself. But the deeper mystery begins when that image is slowly reversed. The brilliant disk grows dimmer. The surrounding galaxy becomes smaller, poorer, and less settled. The stars around it thin into younger populations. The heavy elements that later galaxies take for granted become scarce. Time runs backward through cosmic dawn, and the enormous black hole is stripped of its finished form until only a question remains. What was it when it began? That question is quieter than asking how massive the giant is, but it may be more important. A supermassive black hole is not born already understood just because it is observed already large. Its present size is the last page of a book whose first pages have been burned by distance time and the limits of observation. The word seed sounds small, almost gentle, as if the universe planted something simple in the dark and waited. But in black hole physics, a seed is not a metaphor for certainty. It is the unknown starting mass from which everything else must follow. If the seed was light, perhaps the remnant of one of the first massive stars, then it had to grow with extraordinary efficiency. It had to find gas, keep it falling inward, survive the violence of young galaxies, and gain mass quickly enough to explain the giant seen when the universe was still young. If the seed was heavy, perhaps formed by the direct collapse of a large primordial gas cloud, then the clock becomes less punishing, but another difficulty appears. The universe must first create a rare environment where gas does not behave in the usual way, where it does not fragment easily into many stars, where it can instead fall inward as a single, deepening structure. The first answer is simple. The second answer is stranger. This is why the beginning matters. A black hole does not grow in isolation like a stone quietly becoming larger in empty space. It grows inside a changing universe fed or starved by gas, shaken by galaxy mergers, affected by radiation, surrounded by stars that can heat, stir, and expel the material it needs. Even the phrase rapid growth hides a complicated struggle. Gas falling toward a black hole releases energy, and that energy can push back. The same feeding process that makes a black hole brighter can also make feeding harder. Growth is not just swallowing nearby stars, it is contest between gravity, light motion, and supply. Imagine trying to fill a well while the water rising from the well pushes against the stream flowing in. The image is imperfect, but it carries the feeling of the problem. The seed may be dark, but the act of feeding is luminous, and that light changes the environment around it. When astronomers look at distant active black holes, they're not watching the original seed appear at its birth moment. No telescope has directly seen the first black hole seed being made. Instead, scientists see later clues: hot gas, broad emission lines, compact red sources, galaxies whose centers may already contain growing black holes and light that has traveled across most of cosmic history before reaching us. These clues do not give a single clean answer. They make the old question sharper. The James Webb Space Telescope has made this especially clear by revealing early galaxies and compact red objects in greater detail than before. Some appear consistent with young black holes already feeding in the early universe. Some are difficult to interpret because starlight dust gas and accretion can overlap in ways that are hard to separate. A faint red point is not automatically a black hole. A broad spectral feature is not automatically a complete origin story. The measurement is real. The meaning is harder. Yet the pressure remains. If black holes were already substantial in young cosmic neighborhoods, then their beginnings cannot be ignored. A seed model is like the first marked point on a map. Move that point slightly and the route to the destination changes. A light seed has one route longer, narrower, more dependent on sustained or unusually rapid feeding. A heavy seed has another route shorter in mass distance, but dependent on rarer birth conditions. Mergers add crossings between routes, allowing black holes to combine, but mergers also require time and the right environments. None of these pathways has been proven as the universal answer. The safest view is not that one seed type has defeated all others. It is that the universe may have used more than one method in different places under different conditions with different degrees of success. That makes the story less tidy but more truthful. The first black hole seeds were not labels waiting to be sorted into two boxes. They were physical outcomes of early cosmic conditions, the first stars dying, gas clouds collapsing, radiation fields shaping what gas could do, small galaxies colliding, and matter falling into wells from which light itself could not return. To ask what a supermassive black hole was when it began is to ask what the early universe allowed gravity to build before galaxies became familiar. It is cosmic archaeology, but without bones in the ground. The fossils are spectra red-shifted light mass estimate simulations, and the strange imbalance between a young universe and objects that already seem mature. By the end of the story, the giant black hole may still be the object we see, but the real subject is the missing beginning beneath it. Before the blazing disk, before the galaxy center, before the enormous mass, there had to be some first dark point where collapse became irreversible. That first point may have been small, it may have been massive, it may have belonged to a pathway we can only partly describe, and that is why the next question matters. What kinds of seeds could the early universe actually make? A black hole seed is not a smaller version of the giant in the way a young tree is a smaller version of an old tree. It is a starting condition, a first dark mass inserted into a universe that must then decide whether to feed it, starve it, hide it, or merge it with others. The distinction matters because a supermassive black hole cannot simply appear as a finished object. It must cross a beginning, somewhere before the galaxy center becomes bright, before the gas disk glows, before stars begin tracing fast orbits around an unseen mass. There has to be a moment when collapse makes an object from which no light can return. The later giant may contain millions or billions of solar masses, but the first object did not have to. It only had to exist. That is the quiet pressure behind the seed problem. The universe has no obligation to make the starting point convenient for our models. If the first seed was small, the growth path becomes demanding. If it was large, the birth path becomes demanding. Either way, the giant carries a hidden debt to its origin. At first, the idea of growth feels familiar. Things in nature grow by gathering material. A river grows from tributaries. A planet grows by accreting dust and rock. A galaxy grows by drawing in gas and merging with other galaxies. So it is tempting to imagine a black hole beginning as a modest object and simply becoming larger by taking in whatever falls nearby. But black holes are not open mouths floating through space, casually swallowing everything around them. Most stars pass at safe distances. Most gas has motion that keeps it orbiting rather than falling straight down. Material that does approach the black hole can heat up, shine, and push back on the surrounding flow. Growth is possible, but it is not automatic. That is the problem. A seed is needed because the physics of a black hole begins only after enough mass has already been compressed into a region so small that escape becomes impossible. Ordinary gas clouds, stars, and stellar remnants can approach that condition in different ways, but each route has its own cost. A massive star can collapse at the end of its life and leave behind a black hole. That gives the universe a natural way to make light seeds, especially in the early eras when some stars may have been very massive. But a light seed starts far below the mass of a supermassive black hole. It must then gain mass many times over while the universe is still young, while its host galaxy is still assembling, and while feedback from stars and accretion can disturb the fuel supply. The seed exists, but the clock is tight. A heavy seed changes the arithmetic. If the first black hole begins not as a stellar remnant, but as the result of a much larger direct collapse, then it starts closer to the final giant. It does not need to climb as many orders of mass. The burden shifts from growth to birth. The early universe must arrange a rare environment where a large cloud can avoid fragmenting into ordinary stars and instead collapse toward a massive central object. That is not impossible in theory, but it is not something that can be assumed everywhere. The seed is heavier, but the nursery is more selective. This is why the seed question is not a small detail attached to black hole formation. It controls the entire story. A small initial mass requires powerful growth. A large initial mass requires special formation conditions. A mixed population requires both, plus a way to explain why different galaxies follow different routes. The word seed therefore stores more information than it first seems to. It encodes a beginning, mass, and environment, a formation channel, and a future demand. Change the seed, and the whole timeline changes. A listener can picture this as a long road across darkness. The supermassive black hole is the distant city at the end. A light seed begins near the far horizon, with a much longer path to travel. A heavy seed begins closer, but only if it can first be placed on the road by unusual conditions. Mergers can create shortcuts. Accretion bursts can speed the journey. Starvation can stop it almost completely. The destination may look the same from far away, but the route is written into the invisible history. Astronomers do not usually see that history directly. They infer it from the masses of distant black holes, the ages of their host galaxies, the brightness of accretion, the chemical state of gas, and the number of possible early candidates found in deep surveys. Each measurement is like a broken piece of a map. One piece might suggest a black hole is already large when the universe is still young. Another might show a compact galaxy whose central engine is hard to separate from dense starlight. Another might reveal an active nucleus that seems less massive than the famous quasars, closer perhaps to the missing middle between seeds and giants. None of these pieces alone shows the birth of the first seed. Together they show why the beginning cannot be skipped. The need for seeds is therefore a need for continuity. Scientists are trying to connect the first collapsed object to the later supermassive black hole, without pretending the blank space between them is simple. The connection may involve light seeds growing faster than expected. It may involve heavy seeds forming in rare clouds. It may involve mergers between smaller black holes. It may involve all of these with different weights in different regions of the early universe. The micro-payoff is clear but incomplete. Supermassive black holes are not only massive objects, they are records of starting conditions. Their mystery is not just how they became enormous, it is where the first mass came from, and how much of that mass was already there at the beginning. Before we can follow the feeding, the collisions and the strange red sources Webb now reveals, we have to examine the most natural starting point of all the death of the first massive stars. The most familiar way to make a black hole begins with the star that cannot survive its own weight. In the early universe, before galaxies had settled into their later forms, some of the first stars may have been far more massive than the Sun, made mostly of hydrogen and helium, and born in clouds almost untouched by heavier elements. They lived fast because great mass burns through nuclear fuel with fierce speed. When their cores could no longer support themselves, some may have collapsed, leaving behind black holes. This is the light seed path, and at first it feels almost inevitable. Stars form. Massive stars die. Some deaths leave black holes. The universe by this route does not need an exotic shortcut to begin building darkness. It only needs the first generation of heavy stars to live and end. But the simplicity fades as soon as the seed is placed on the timeline. A stellar collapse remnant may be a real black hole, yet it is still small compared with the giants that later sit in galactic centers. The word light does not mean unimportant. It means that the seed begins with a long climb ahead. A seed formed from a massive early star may start with tens, perhaps hundreds, or in some models more solar masses, but a supermassive black hole contains millions or billions of solar masses. The distance between those numbers is not a gap that can be crossed by imagination. It has to be crossed by physics. The seed must accrete gas, perhaps merge with other black holes, and remain in environments where fuel continues to arrive. It must do this while the first galaxies are young, irregular, and violent. That is where the natural beginning becomes a difficult journey. A light seed is easy to motivate but hard to grow quickly enough in every case. The first stars themselves are not directly visible as ordinary individual objects from the earliest cosmic times. Scientists infer their properties through theory, simulations, chemical evidence, and the later imprint they may have left on galaxies and intergalactic gas. These stars are often called population 3 stars, meaning a hypothetical first stellar generation formed from nearly pristine material. With fewer heavy elements, their gas may have cooled differently from gas in later galaxies, allowing some stars to form at very high masses. Yet this picture is not a simple factory making identical seeds. Some early stars may have exploded completely, leaving no black hole at all. Some may have left smaller remnants, some may have collapsed more directly. The outcome depends on mass rotation, environment, and the physics of the star's final stages. The seed is not guaranteed. It is conditional. Imagine an ancient forest after a storm, but instead of fallen trunks, each ending leaves a dark pit in the soil only if the conditions were right. Some places receive seeds, some do not. Some seeds are carried into richer ground. Others fall where nothing feeds them. The comparison is imperfect because black holes are not alive and do not grow like plants, but it captures the unevenness of the early universe. A light seed born in a poor location might remain small for a long time. A similar seed born inside a dense gas flow might grow faster. Another might be pushed away from the center of its small galaxy by the recoil of a supernova, or by gravitational interactions losing access to fuel. The beginning is only the beginning. Location matters. This is why light seeds create both comfort and pressure in black hole origin stories. They are comfortable because they arise from known astrophysical processes. Stars collapse today. Stellar mass black holes are observed in the modern universe. The early universe likely made massive stars, and some of those stars plausibly left remnants. No rare direct collapse event is required to make the first black hole in this pathway, but the pressure appears when astronomers compare possible starting masses with the existence of large black holes at early cosmic times. If a young black hole is already large, a light seed must have grown efficiently, perhaps near the limit allowed by radiation pressure, perhaps above that limit for short phases, perhaps in thick flows where radiation escapes unevenly. The easy origin demands a demanding adolescence. The science turns on a quiet distinction. Making a seed and making a giant are not the same problem. A light seed may be common, but common beginnings do not automatically make supermassive endings. Most small black holes may never become central giants. They may wander, merge, starve, or remain hidden. The ones that succeed may be a selected minority, those born in rare places where gas supply and galaxy growth work together. That means a universe filled with light seeds could still produce only some of the supermassive black holes we observe, unless the growth conditions were favorable often enough. The seed model cannot be judged only by whether it can make a black hole. It must also explain the population. How many should exist? How massive should they be? How bright should they become? What kind of host galaxies should surround them? A single distant object cannot answer all of this. It can only apply pressure. The micro-payoff is that the light seed path is not weak because it is small. It is powerful because it is natural and uncertain, because nature does not promise enough time, enough gas, or enough efficiency. It offers the universe a simple first dark point, then asks the environment to do the hard work afterward. This is why light seeds remain central to the debate. They connect black hole origins to the first stars, to early chemical history, and to the ordinary fact that massive stars can die into darkness. But they do not end the story. If some early black holes appear too massive too soon, or if their host galaxies seem too small for their central engines, then scientists must ask whether certain black holes began with a much larger gift. The next path does not start with the star dying. It starts with gas trying not to become stars at all. There is a more radical way to begin a giant black hole. Do not begin with the death of a star. Begin with a cloud. Imagine the early universe before many heavy elements exist, when gas is mostly hydrogen and helium gathered inside a young dark matter halo where gravity is trying to pull everything inward. In the ordinary story, that cloud cools, breaks into clumps and forms stars. The stars then live, burn, collapse, and only afterward do some black holes appear. Direct collapse asks whether in rare places the cloud could avoid that familiar route. Instead of fragmenting into many separate stars, a large flow of gas might keep falling toward the center, building a massive object so quickly and so deeply that a heavy black hole seed becomes possible. The appeal is immediate. If the first seed begins much larger than a stellar remnant, it does not need to grow across such a punishing distance before the universe becomes old enough for astronomers to see it as a young giant. It begins with a head start, but the head start is bought with difficulty. The universe must stop gas from doing what gas usually does. At first, direct collapse sounds like gravity simply winning. A cloud is massive. Gravity pulls. Matter falls inward. A black hole forms. But real clouds are not smooth, obedient spheres. They spin. They cool. They stir. They form knots and filaments. They can split into many centers of collapse, and each center can become a star. Cooling matters because it lets gas lose heat and settle into smaller structures. In a later galaxy where heavier elements and dust are available, cooling can be efficient and fragmentation becomes easier. In very primitive gas, cooling is more limited but not absent. Hydrogen can still help gas shed energy under some conditions. Molecules can form. Local density can rise. The cloud can become uneven. This is where the shortcut becomes delicate. To make a heavy seed, gravity must not only pull hard, it must pull in a way that keeps the collapse coherent. That is the hidden complication. Some direct collapse models require intense radiation from nearby young stars or galaxies to prevent molecular hydrogen from cooling the gas too effectively. If that cooling is suppressed, the gas may remain warmer, less likely to fragment into many small stellar clumps, and more likely to flow inward on a larger scale. Other models explore how turbulence, rapid, inflow halo growth and radiation feedback could shape the same outcome. None of this means direct collapse has been watched as it happens in the first universe. It means theorists have identified physical pathways where a heavy seed could form if the environment is rare and carefully arranged. The word rare matters. A model can be plausible without being common. Picture a mountain stream after rain. Most of the water divides into channels, eddies, side paths, and small pools. Only under certain slopes and boundaries does the flow stay concentrated enough to carve one deep route. A primordial gas cloud is not water, but the image helps. Direct collapse needs a large inward flow that does not dissolve into too many smaller stories. If the gas fragments stars appear, and the heavy seed route may be interrupted. If stars appear, their radiation and explosions can heat or expel gas, changing the central collapse. If angular momentum is too large, gas settles into a disk or orbiting structure instead of falling straight inward. The conditions are not magical, but they are demanding. A heavy seed may therefore be less like an ordinary seed planted everywhere and more like a rare geological formation created only where pressure, composition, flow, and timing align. The scientific turn is that heavy seeds solve one problem by moving it earlier. They ease the growth problem because the black hole begins larger. A seed that starts with a much greater mass can reach supermassive scales with fewer doublings, especially if accretion is steady or occasionally rapid. But the formation problem becomes sharper. How often did the early universe create the special conditions needed? Did enough pristine or nearly pristine gas clouds exist near the right radiation fields? Could large halos assemble without fragmenting too soon? These are not decorative details. They decide whether heavy seeds were a rare curiosity, a major pathway, or one part of a broader population. The evidence remains indirect. Astronomers can search for young black holes whose masses seem high, Compared with the ages or stellar masses of their host galaxies, they can study compact red sources whose light may contain signs of accretion hidden behind gas. They can compare populations with simulations that predict how many heavy seeds should exist under different assumptions. But seeing a candidate descendant is not the same as seeing the birth. A distant object that looks consistent with a heavy seed may still have another explanation. It could be a light seed that grew unusually fast. It could be a complex blend of stars, gas dust, and accretion. The measurement may point toward a massive beginning, but it does not force one. This caution is not a weakness. It is what keeps the story honest. The micro payoff is that the heavy seed pathway is not simply a bigger version of the light seed pathway. It is a different bargain with the early universe. Light seeds are easier to make but harder to grow quickly. Heavy seeds are easier to grow into early giants, but harder to make in the first place. One begins with stellar death and asks for efficient feeding. The other begins with unusual gas collapse and asks for rare birth conditions. Neither has been proven as the answer for all supermassive black holes, and the most truthful picture may include both. Yet the heavy seed idea changes the emotional shape of the mystery. It suggests that some black holes may not have climbed all the way from small beginnings. Some may have been given a dark foundation already large enough to matter. But to understand whether that foundation can really form the next question must move inside the cloud itself. Gas does not collapse as a silent curtain. It resists, cools, spins, breaks, and shines. The shortcut only works if the cloud refuses simplicity. A gas cloud looks simple only from far away. In an image made for the imagination, it may appear as a dark blue mist hanging in the early universe, slowly tightening under its own gravity, as if collapse were a calm and inevitable descent. But inside the cloud, nothing is calm. Every part of the gas has motion. Some parts fall inward, some orbit, some collide and heat, some cool and become denser. Small differences grow into knots, and knots can become stars. The cloud is not one object deciding to become one black hole. It is a restless system with many possible futures, and direct collapse requires one of the rarest futures to win. This is why the heavy seed story cannot stop at the phrase large gas cloud. The phrase hides the actual battle. Gravity wants to gather the cloud, but physics gives the cloud many ways to divide itself before the center can become deep enough. At first, the basic force seems obvious. Gravity pulls every parcel of gas toward every other parcel. If enough mass collects in a young halo, the central region becomes denser, and denser gas can fall faster. But gas has pressure, and pressure resists compression. Gas also heats as it is squeezed, and hotter. Gas pushes outward more strongly. For collapse to continue, the gas often needs to lose energy. It must cool. Cooling sounds helpful because it lets material settle inward, but in the seed problem, cooling can become the enemy of a heavy beginning. When gas cools efficiently, it can fragment into smaller clumps. Each clump can collapse on its own. Instead of one central flow feeding a massive object, the cloud becomes a nursery of stars. The black hole seed may still appear later, after some stars die, but then the route has changed. The direct collapse shortcut has been lost. The meaning is subtle. Heavy seeds do not require gravity alone. They require gravity with just the right resistance to fragmentation. In primordial gas, one important cooling pathway involves molecular hydrogen, a simple molecule that can radiate energy away and allow gas to settle into smaller structures. If radiation from nearby young stars or galaxies breaks apart enough molecular hydrogen, the cloud may remain warmer. Warmer gas can resist fragmenting into many small pieces, keeping more mass available for a central inflow. This does not guarantee a black hole. It only makes one pathway more plausible. The surrounding radiation field must be strong enough, the halo massive enough, the timing favorable enough, and the gas inflow sustained enough. A slight change in any of the conditions can alter the result. A seed pathway is not a button pressed by the universe. It is an outcome balanced on many linked processes. Rotation adds another complication. A cloud cannot usually fall straight inward, because even a small amount of spin becomes important as the cloud contracts. The same reason a spinning skater turns faster when pulling in their arms applies in a distant, colder, more ancient form. As gas moves inward, its angular momentum can make it settle into a disk, orbiting, rather than plunging directly into the center. Disks can still feed central objects, but they can also become unstable forms, spiral arms, break into clumps and produce stars. The flow may look like a river from a distance, but near the center it behaves more like traffic at a crowded junction, with streams crossing, slowing, heating, and redirecting one another. The central question becomes not merely whether gas is present, but whether the gas can lose enough angular momentum without losing the coherent inward flow required for a heavy seed. Turbulence makes the picture even less tidy. The early universe was not a perfectly smooth laboratory. Gas fell along filaments, dark matter, halos, merged shock waves formed, and young stars could flood nearby regions with radiation. Turbulence can sometimes help drive gas inward, but it can also stir the cloud seed irregularities and encourage fragmentation. Feedback from the first stars can heat or expel gas. Radiation from an accreting object, if one begins to form, can push back on the surrounding material. The forming seed may disturb its own cradle. That is the hidden tension. The environment that feeds the seed may also fight it. This is why simulations are so important in seed research. They allow scientists to test how gas behaves under different early conditions, but simulations are not direct observations. They depend on assumptions about cooling, radiation, chemistry, turbulence, and resolution. A model can reveal a pathway that obeys known physics, but it cannot by itself prove how often nature used that pathway. Astronomers then look for descendants, early active black holes, compact red sources, unusual black hole to galaxy mass ratios, or populations that seem too numerous or too massive for one simple route. The test is indirect, like hearing a distant bell and trying to reconstruct the shape of the room that rang it. The cloud itself is gone. The birth moment is hidden. Only later light remains. The micro payoff is that direct collapse is not a magical exception to star formation. It is a narrow channel through the same physics that normally makes stars. It asks whether in rare early halos gas could stay warm enough, inflow could remain strong enough, rotation could be managed well enough, and fragmentation could be delayed long enough for a massive central object to appear. Each condition is understandable. Together they are demanding. This is why heavy seeds are compelling but not settled. They give some early black holes a possible head start, but they do not remove mystery. They relocate it into the behavior of gas before the seed is born, and once a seed exists, light or heavy, the next struggle begins immediately. It must grow. It must feed in a universe that may offer abundant gas but never offers it without resistance. The question is no longer only how a dark point forms. It is how that dark point eats while its own brightness pushes the meal away. Once a black hole seed exists, the universe gives it a paradox. The same gas that can make it grow can also make growth harder. Matter falling toward a black hole does not usually drop straight into darkness like rain into an open well. It spirals, collides, heats, and forms a bright, restless disk. The deeper the gas falls, the more gravitational energy it releases, and that energy emerges as radiation. A young black hole that feeds well can therefore become luminous, even though the black hole itself remains dark. But light has pressure. It can push on gas. It can heat the surrounding material. It can help drive winds away from the center. The seed is trying to gain mass through infalling fuel, while the glow of that fuel pushes back against the next material arriving. This is the quiet contradiction at the center of black hole growth. Feeding makes the engine brighter, and brightness can make feeding less efficient. At first, this seems like a simple limit. If gravity pulls inward and radiation pushes outward, there should be a balance point. In basic terms, that balance is often associated with the Eddington limit, a useful way to describe how rapidly a black hole can steadily accrete when outward radiation pressure competes with inward gravity. The name can sound technical, but the idea is physical and almost visual. Imagine a lamp at the bottom of a dusty funnel. The stronger the lamp shines, the harder it becomes for more dust to fall inward through the light. Gravity keeps drawing the dust down, but the light presses upward. A black hole is not a lamp, and cosmic gas is not dust in a room, but the comparison captures the pressure. Accretion is not only a supply problem, it is also a feedback problem. The seed changes the environment that feeds it. For light seeds, this matters enormously. If a black hole begins small and must become very large, while the universe is still young, then slow and gentle feeding may not be enough. It may need long periods of efficient accretion, short periods of especially rapid accretion, or both. If it grows only at a conservative, steady rate and loses too much time to starvation disruption or feedback, it may fail to reach the masses inferred for some early active black holes. The seed could be real and still not become a giant. The clock does not forgive empty intervals. Heavy seeds feel less pressure from this particular clock because they start larger, but they are not free from the feeding problem. A massive beginning still needs gas to cross the final distance to supermassive scale, and the same radiation struggle applies. A head start reduces the journey. It does not erase the terrain. The hidden complication is that the Eddington idea is not a simple wall in every real environment. It is a guide, not a complete description of all possible growth. Gas can be thick, clumpy, asymmetric, magnetized and turbulent. Radiation may escape more easily in some directions than others. Dense inflows may shield themselves. Disks may become puffed up rather than thin and orderly. Some models allow super Eddington accretion, where mass falls in faster than the simplest steady picture would suggest, at least for limited times or under special geometries. This does not mean black holes can grow without constraint. It means the constraint depends on how the gas is arranged, how radiation escapes, and how long the conditions last. The easy version says there is a speed limit. The deeper version asks what kind of road the seed is travelling on. A young galaxy may provide a road unlike the calm centres of mature galaxies. Early galaxies were rich in gas, more compact and more disturbed by inflows and mergers. Streams of material could fall into them along cosmic filaments. Star formation could stir and heat the gas, while gravity tried to pull it inward again. A black hole seed near the centre might experience alternating phases: abundance, disruption, burial clearing, and renewed inflow. Its growth may have been episodic rather than smooth. For a listener, this is like imagining a small fire in a storm, sometimes smothered, sometimes fed by sudden gusts, sometimes hidden under smoke, sometimes flaring bright enough to change the air around it. The black hole is not fire, but the rhythm of feeding and feedback has a similar instability. What matters is not only the average supply, but the timing of the bursts. This is where rapid accretion becomes important without becoming magical. It may help explain how certain seeds grew faster than simple limits suggest, especially if the accretion flow was dense enough and shaped in a way that allowed radiation to escape unevenly. But rapid accretion cannot be invoked as a universal shortcut without evidence. It must be connected to realistic gas supplies, host galaxy conditions, and observable consequences. A rapidly feeding black hole should leave traces luminosity ionized, gas broad spectral features, outflows heat, and perhaps a mismatch between the black hole and its surrounding stars. Webb and other observatories search for such traces in early galaxies, but interpretation remains difficult because young stars, dust gas, and accretion can all contribute to the light. The micro payoff is that black hole growth is not a matter of hunger alone. It is a regulated struggle in which gravity, radiation, geometry, and environment negotiate how much mass can actually cross the event horizon. A seed can sit in a gas-rich universe and still grow slowly if the gas cannot lose angular momentum, if feedback clears the center, or if fuel arrives in the wrong pattern. Another seed born in a favorable place might pass through intense growth episodes and become disproportionately massive compared with its galaxy. This difference is why the same type of seed can have different fates. The birth mass matters, but the feeding history can reshape the entire outcome. The next question, therefore, becomes more subtle than whether a seed can feed. It is whether short extreme episodes of feeding could rescue the smallest beginnings and let light seeds catch up before cosmic time runs too far ahead. A light seed begins with a disadvantage so severe that the universe almost seems to be asking too much of it. If a black hole starts as the remnant of an early massive star, it has already crossed the first threshold, but it has not crossed the main distance. It must gain mass again and again, multiplying itself through gas, time, and circumstance, until it becomes something that can anchor the center of a galaxy. In a slow, steady picture, this is difficult for the earliest giants. The clock is short, the galaxies are young, and the feeding process pushes back through radiation. But the universe is rarely steady. It builds in surges. Gas falls along filaments. Small galaxies collide. Dense clouds lose support and rush inward. A seed that starves for long stretches may suddenly find itself buried in fuel. The question is whether such burst could change the fate of the smallest beginnings. This is where light seeds become more interesting than they first appeared. Their weakness is obvious: they begin small. But if the early universe could deliver gas in intense episodes, then small beginnings might not always stay small. A black hole does not need to feed at a perfect rate across every moment of its life. It may grow in chapters. Long quiet intervals can be followed by short phases of rapid inflow, when gas piles toward the center faster than a simple, thin, orderly disk would suggest. In those moments, the geometry of the flow matters. A thick disk or dense envelope may trap radiation, redirect it, or allow it to escape along certain paths, while material continues falling from other directions. The phrase super-Eddington accretion can sound as if a law is being broken, but that is not the careful meaning. It means that under particular conditions, mass may be supplied to the black hole faster than the simplest steady balance would predict. The physics is not abandoned, it becomes more complex. The hidden complication is duration. A burst that is possible for a short time does not automatically solve a growth history. To transform a light seed into an early supermassive black hole, rapid feeding must happen often enough, long enough, and in the right environment. The gas supply must be deep. The central region must keep delivering material. Feedback must not permanently clear the fuel. The black hole must remain near the dense center, rather than being displaced by stellar explosions, gravitational encounters, or mergers. A spectacular burst that ends quickly may leave only a modest gain. A weaker but repeated sequence of bursts could matter more. Growth depends not only on how fast a black hole feeds at its brightest, but on how much of its life is spent in that state. A sleeping seed does not grow. This makes early galaxies crucial. They were not quiet disks with neat spiral arms and settled centers. Many were compact, irregular, and gas-rich, shaped by inflows from the cosmic web and by frequent encounters with other young systems. Their centers may have been unstable places where gas could be driven inward by turbulence bars, clumps, or mergers. For a black hole seed, such disorder could be dangerous or useful. It could scatter fuel away, or it could push fuel down into the central region. It could bury the seed behind dense gas, making it difficult to observe, or it could feed the seed until radiation and winds opened channels through the surrounding material. The same chaos that threatens steady growth may create the bursts that make rapid growth possible. Imagine a dry riverbed that receives no water for months, then suddenly fills during a storm. The annual average matters, but so does the flood. A black hole seed in an early galaxy may have grown in a similarly uneven rhythm, not because the comparison is physically exact, but because it shows why averages can hide decisive moments. If scientists estimate growth only by assuming smooth feeding, they may underestimate what short, dense inflows can do. But if they invoke bursts too freely, they risk replacing one difficulty with an untested convenience. The challenge is to find observable traces. Rapid accretion should not be invisible. It can heat gas, produce broad emission features, drive outflows, and make a compact source shine in ways that compete with or overwhelm the light from young stars. Yet at extreme distances, the signals blur together. Dust can redden starlight. Dense gas can hide an active nucleus. Starbursts can mimic some signs of energetic activity. A faint red source may contain a feeding black hole, but the light has to be separated carefully before the seed story can be trusted. The micro payoff is that rapid accretion gives light seeds a possible rescue, but not a free escape. It does not prove that all early giants grew from small remnants. It shows that the gap between light seeds and supermassive black holes may be narrowed if feeding was bursty dense and geometrically favorable in some early galaxies. That is a meaningful opening. It allows small beginnings to remain in the conversation without pretending the problem has vanished. It also makes the seed debate less rigid. A light seed with ordinary slow feeding may struggle. A light seed with repeated rapid episodes may compete with a heavier beginning. A heavy seed with poor feeding may stall. A smaller seed in the right galaxy may outrun a larger seed in the wrong one. The origin is not only written in the birth mass, it is written in the weather of gas around the seed, and still accretion is only one way to climb. In a universe where galaxies merge, their central black holes may eventually meet as well. Growth may come not only from gas falling inward, but from darkness joining darkness. Growth by collision sounds almost too clean, as if the universe could solve the seed problem by letting small black holes find one another in the dark. Young galaxies merge, their stars mix, their gas is shaken into new shapes. If each galaxy carries a black hole seed near its center, then two seeds may eventually become one larger black hole. In this picture, the early universe behaves like a gathering system, turning many small beginnings into fewer heavier ones. The appeal is clear. A light seed does not have to do all of its climbing by gas alone. A heavy seed does not have to remain solitary. Every merger can add mass, and in the long assembly of galaxies, mergers are not exotic. They are part of how structure grows. But the simple image hides a slower and more difficult path. Two galaxies can merge long before their black holes actually touch. The collision of galaxies is not the same as the collision of the dark objects inside them. That distinction matters. When galaxies come together, their stars mostly pass one another across vast empty spaces, while gas can compress shock and flow inward. The black holes, if they are present, may sink toward the new center through gravitational interactions with stars' gas and dark matter. But sinking takes time. They must lose orbital energy. They may form a pair, then a tighter binary, then finally approach close enough that gravitational waves carry away the last energy and the two horizons become one. Each stage can be delayed. The merger is not a single moment stretched across a beautiful animation. It is a sequence of negotiations with the surrounding galaxy. That is the complication. A black hole merger can be powerful, but it is not instant. For the earliest supermassive black holes, time is precisely what seems scarce. If mergers are to matter, they must happen in environments dense enough and efficient enough to bring seeds together quickly. Small early galaxies may merge often, but their black holes may also be small, wandering, or displaced from the center. Some seeds may never meet another seed. Some may be kicked by gravitational recoil after an uneven merger, moving away from the dense gas that would have fed them. Some may remain in satellite galaxies or star clusters invisible to ordinary surveys. A merger pathway can add mass, but it also creates a population of failures, wanderers, and delayed encounters. The universe does not collect every dark seed neatly into one final giant. Imagine two stones dropped into a deep pond from opposite sides. They belong to the same pond, but they do not automatically meet at the bottom. Current, slopes, obstacles, and time decide whether they settle together. In a young galaxy, the equivalents are gravity, gas drag, stellar scattering turbulence, and dark matter. The black holes are not steering themselves toward a destiny. They are carried by a changing environment. This is why mergers are best understood as one channel in a larger system, not as a simple replacement for accretion. Even after two black holes become one, the new object may still need gas to continue growing. A merger can double mass under favorable circumstances, but many doublings are needed to reach the larger scales if the starting objects are small. Gas remains central, accretion remains central, birth mass remains central. Mergers change the ladder, but they do not remove the ladder. The scientific turn is that mergers may be most important when combined with feeding. A galaxy merger can drive gas toward the center, triggering star formation and possibly increasing the fuel supply for a black hole. The same event that brings black holes closer can also disturb the gas around them. In some cases, this may help accretion. In others, feedback may expel gas and slow growth. A collision of galaxies is therefore not just an addition problem. It can rearrange the entire feeding environment. It can create a denser central region, or it can make the system more chaotic. It can help two seeds become one, or it can scatter the conditions that would have allowed either seed to grow. The evidence for black hole mergers comes from several directions. In the nearby and intermediate universe, astronomers observe interacting galaxies, dual-active galactic nuclei, and systems that suggest black holes can coexist and eventually merge. Gravitational wave observatories have detected mergers of stellar mass black holes, proving that black holes can spiral together and combine. Future space-based gravitational wave missions are expected to be especially important for massive black hole mergers because the waves from larger systems stretch into lower frequencies than current ground-based detectors can best hear. For the earliest seeds, much remains inferred. Scientists use simulations to estimate how often small galaxies merged, how quickly their black holes sank, and how many mergers should occur under different seed models. These predictions can then be compared with the later observations, but the early record is still incomplete. The micro payoff is that mergers are real, necessary, and insufficient by themselves. They offer a way to build mass by combining black holes, and they naturally fit into a universe where galaxies assemble from smaller pieces. But they do not erase the need for seeds, and they do not eliminate the need for accretion. They add another path through the maze. A giant black hole may carry the memory of many smaller black holes inside it, just as a large river contains streams that once had separate names. Yet the river also depends on rain, terrain, and time. In the same way, a supermassive black hole may grow through mergers, but its final mass also depends on gas supply, birth mass feedback, and the host galaxy's history. This makes the origin story richer and less tidy. A light seed can grow by bursts of gas and occasional mergers. A heavy seed can merge with other seeds and then accrete. Different early galaxies may have followed different combinations. The question becomes less about choosing one process and more about weighing their roles. But to weigh them properly, we have to move outward from the seed itself. The next layer is the nursery, the first galaxies where gas stars, dark matter, and black holes either worked together or pulled the young seed apart. The first galaxies were not quiet homes waiting for black hole seeds to settle at their centers. They were young, compact, irregular systems still assembling from gas dark matter stars and smaller clumps falling together in the expanding universe. Their shapes were not the grand spirals familiar from nearby cosmic images. They were more like unfinished workshops, dense in some places, empty in others, lit by new stars stirred by explosions and crossed by streams of gas, arriving from the larger cosmic web. A black hole seed born inside such a place did not grow only because it existed. It grew stalled, wandered, or vanished from view depending on the nursery around it. This is why the seed problem cannot be solved by looking at the seed alone. The cradle matters. A light seed in a rich gas-driven center may grow faster than expected. A heavy seed in a disturbed or starving system may lose its advantage. The same beginning can have different futures. At first, a galaxy seems like a container. It holds stars, gas dust, dark matter, and perhaps a central black hole. But in the early universe, the container was still being built while the seed was trying to grow. Gas fell in along filaments, not as a smooth rain, but as uneven flows. Clumps merged. Stars formed in bursts. Radiation from young stars heated nearby gas. Supernova could blow material outward, while gravity later drew some of it back in. The black hole seed sat inside this changing weather. If dense gas reached the center, the seed might feed. If stellar feedback cleared the center, it might starve. If a merger disturbed the galaxy, it might drive gas inward or throw the seed away from its best fuel. The nursery was not a background. It was an active participant. This creates a hidden complication in the way astronomers interpret early black holes. When a distant object appears to contain a growing black hole, scientists also need to know the host galaxy around it. How many stars does the galaxy contain? How much gas is present? Is the black hole unusually massive compared with the stellar system, or roughly in line with later patterns? Is the light dominated by young stars, hot dust, or accretion near the black hole? These questions are difficult because the objects are faint and far away. Webb can stretch the reach of infrared astronomy, but even Webb does not hand over a clean diagram with labels. Light from stars and light from a feeding black hole can overlap. Dust can redden both. Gas can glow in lines that reveal motion and ionization, but those lines must be interpreted carefully. The image is small. The physics behind it is large. Think of an early galaxy as a tide pool during a storm, not because the scale is similar, but because the conditions change quickly and many small interactions decide what survives. A seed near the deepest part may be covered again and again by waves of gas. Another seed, only a short distance away in cosmic terms, may sit in a region cleared by stellar explosions. One may become bright enough to announce itself as an active nucleus. Another may remain dark, not because it is absent, but because it is not feeding strongly. This matters for surveys. Observatories find the black holes that shine or the galaxies whose light carries detectable signatures. They may miss quiet seeds, starved seeds, wandering seeds, or seeds buried so deeply that their radiation cannot easily escape. The visible population may be only the tip of a hidden population. The scientific turn is that early black hole growth is a coevolution problem from the beginning. In later galaxies, astronomers see broad relationships between central black holes and the stellar bulges around them, though these relationships have scatter and complicated histories. In the early universe, those relationships may still be forming. Some Webb candidates raise the possibility that black holes grew early relative to their host galaxies, though each case must be tested cautiously. If true for part of the population, this would mean black holes were not merely passengers inside galaxies. They may have influenced gas star formation and central structure very early. But the reverse is also true. Galaxies controlled the fuel confinement and merger history of the seeds. The black hole shaped the nursery and the nursery shaped the black hole. Neither story is complete without the other. This is why seed models make predictions not just about black hole masses, but about environments. A light seed-dominated universe might produce many small remnants with only a fraction growing efficiently in favorable galaxies. A heavy seed pathway might produce fewer but initially larger objects, perhaps in special halos exposed to particular radiation conditions. Rapid accretion models might predict compact, gas-rich hosts with buried or unusually bright central engines. Merger-heavy histories might leave signs in galaxy structure, or eventually in gravitational wave backgrounds and events. These predictions are not simple labels stamped onto individual objects. They become meaningful across populations. One galaxy can mislead. Many galaxies can begin to reveal a pattern. The micro-payoff is that the first galaxies were not merely the scenery around black hole seeds. They were nurseries, filters, engines, and obstacles. They decided which seeds had access to gas, which remained small, which moved toward the center, which were buried, and which became visible to distant telescopes. A seed's fate was written partly in its birth mass, but also in the architecture of its host. This makes the mystery more difficult, but also more testable. If scientists can measure both the black hole and the galaxy around it, they can begin to compare the route each object may have taken. The next question follows naturally from this. Webb has begun to reveal early systems where the balance between black hole and galaxy may not look familiar. To understand why that matters, we have to see how infrared light made the seed problem sharper, and why faint red sources have become some of the most important clues in the search for beginnings. Webb did not create the black hole seed mystery, but it changed the feeling of it. Before Webb, astronomers already knew that very distant quasars contained enormous black holes when the universe was young. Those bright objects were like lighthouse beams, from rare systems powerful enough to be seen across deep time. They proved that some black holes had grown early, but they did not show the quieter population beneath them. Webb opened a different window. By looking in infrared light where the stretched light of the early universe arrives, it began finding faint galaxies, compact sources, and active black hole candidates closer to the missing middle between seed and giant. The image did not suddenly become simple. It became more crowded with clues. That is what made the problem sharper. A mystery is sometimes deepened not by darkness, but by better sight. The reason infrared matters is tied to cosmic expansion. Light from the early universe begins its journey at shorter wavelengths, but as space expands, the light is stretched. By the time it reaches a telescope near Earth, much of that ancient light has shifted into the infrared. Webb was built to collect that kind of light with extraordinary sensitivity. For early black hole studies, this matters because the relevant objects are faint small in the sky and blended with their host galaxies. A feeding black hole can reveal itself through hot gas near the center. Broad spectral features, ionized material, or unusual brightness compared with surrounding stars. But those signatures are subtle when the object is young and distant. Webb does not see the seed being born. It sees later phases that may sit closer to the beginning than the brilliant quasars known before. The distinction is crucial. One important example is the discovery of early active black holes in deep Webb surveys, including sources described as lower mass or less extreme than the famous high redshift quasars. Objects like C, EE, RS 1019 are valuable because they suggest astronomers may be reaching a population that connects the first seeds to later giants. They are not the first dark points themselves. They are possible descendants at a stage when the black hole may still be growing rapidly inside a young galaxy. That makes them archaeological fragments. A giant quasar is like finding a finished palace in an ancient ruin. A fainter early active black hole is more like finding a foundation stone close to the era of construction. It does not tell the whole story, but it changes where the excavation can begin. Then came the compact red sources often called little red dots. The nickname is simple, almost harmless, but the interpretation is not. In Webb images, some of these objects appear small and red, and their spectra can suggest dense gas, unusual compactness, and in some cases possible accretion by a central black hole. They may represent young galaxies containing growing black holes, perhaps partly hidden in gas and dust. Some studies interpret them as signs that black holes could be surprisingly massive compared with their young host galaxies. Other interpretations remain possible, including unusual stellar populations, dense star-forming systems, or stages involving very massive stars and heavy seed formation. The dot is not the answer. It is the place where several answers overlap. This is why Webb's role is not to declare one seed model victorious. It is to create new tests. If many early objects contain black holes that are already large compared with their host galaxies, heavy seeds or rapid growth become more attractive. If lower mass active black holes are common and follow growth tracks consistent with stellar collapse beginnings, light seeds remain plausible. If the population shows a wide spread with some objects overmassive, some modest, some buried, and some starving, then the universe may have used several pathways. The measurement does not solve the mystery. It narrows the hiding places. The hidden complication is that early light is crowded with imposters and mixtures. Young stars can be extremely bright before that light is stretched into the infrared. Dust can redden a galaxy and make it appear older or more active than it is. Gas heated by stars can produce emission lines, while gas near a black hole can produce different, but sometimes overlapping signals. A compact source may look black hole dominated, but the stellar contribution may be larger than expected. Or the reverse may happen. A feeding black hole may be buried inside light, that at first seems mostly stellar. Astronomers therefore need spectra models, repeated comparisons and observations across multiple wavelengths. Webb provides a powerful part of this, but not the entire answer. X-ray observations, radio data, gravitational wave prospects and simulations all become part of the larger framework. For a human-scale image, imagine hearing a single instrument inside a distant orchestra through a wall. Better equipment may let you hear more detail, perhaps the low note of a cello or the pulse of a drum. But the sound still arrives blended. To decide which instrument is playing, you need tone, rhythm, timing, and comparison with the rest of the music. Webb gives astronomers a clearer sound from cosmic dawn, but they still have to separate black hole accretion from stars' dust and gas. That separation turns small red points into physical questions. How massive is the central black hole? How fast is it feeding? How large is the host galaxy? And what kind of seed history could lead to this combination? The micro payoff is that Webb makes the seed problem more urgent because it moves the search from rare brilliant giants toward dimmer younger systems where beginnings may leave stronger traces. It does not show the birth of the first seed. It does not prove that every early black hole came from direct collapse. It does not prove that light seeds grew fast enough everywhere. Instead, it reveals a landscape where those models can finally be pressured by data. This is progress without a final answer. The next difficulty is that some of the most interesting clues, the little red dots, sit exactly at the boundary between categories. To follow them, we must enter the ambiguous place where a tiny red source may be a young black hole, a dense galaxy, a hidden accretion engine, or something stranger still. The little red dots are troubling because their name makes them sound simple. In a deep Webb field, they can appear as tiny red points, almost like quiet specks of colour scattered among faint galaxies. But a small image can hide a large argument. Their redness may come from distance dust, old or unusual stars, hot gas around a feeding black hole, or several of these at once. Their compactness may suggest something dense and central, but compact light is not the same as a direct photograph of an event horizon. Their spectra can show features that look consistent with accretion, yet spectra are also shaped by gas stars' motion and the limits of separating one source from another across cosmic time. The dot is visible. The identity is not. This is why little red dots have become so important to the seed problem. They may occupy the shadowy interval between the first dark seed and the obvious supermassive quasar, but they do not announce which pathway made them. At first, the tempting answer is that many little red dots contain young black holes. Some show signs that can be interpreted as broad emission from fast-moving gas near a central engine. Some appear too compact or too luminous in ways that invite an accretion explanation. Some may contain black holes that seem unusually massive compared with the young galaxies around them. If that interpretation holds for a significant part of the population, the seed question becomes more urgent. A black hole that is already prominent inside a small early galaxy may hint at a heavy beginning, rapid growth, or both. It may suggest that the central dark object formed and gained influence before the host galaxy built a familiar stellar body around it. But this is not proof of one origin. It is a clue with several possible histories attached. The same observation can be consistent with more than one route. The hidden complication is that early galaxies are extreme laboratories. Their stars may be young, dense, metal-poor and arranged in compact systems. Their gas can be thick and strongly ionized. Their dust content may be uncertain. Their light can be reddened by cosmic expansion and by material inside the galaxy itself. A population of unusual stars may imitate some of the colors expected from accretion. A buried black hole may imitate a dense stellar system. A central object wrapped in gas may appear different from a clean, bright quasar. Even the apparent mass of a black hole depends on how scientists interpret line widths, luminosity's geometry, and the balance between starlight and accretion light. The measurement is not empty, but it is layered. Each layer has to be peeled away with caution. One of the most intriguing possibilities is that some little red dots could represent black holes in a cocoon stage still surrounded by dense gas from their early growth. In that picture, the central engine is present but not yet exposed like the brilliant quasars of later cosmic time. The black hole may be feeding inside a compact young galaxy with gas absorbing, reprocessing, and reddening the light. Such an object would be valuable, because it could show a growth phase closer to the seed era. It would not show the seed being born. It would show something after birth, but before maturity, a stage when the route from seed to giant might still be written in the surrounding gas. For cosmic archaeology, that is precious. A foundation is not the first stone cut from the mountain, but it is closer to the beginning than a finished tower. Another possibility is stranger but still scientific. Some objects may involve very massive stars or star-like configurations, connected to the conditions that could precede heavy seed formation. These ideas remain under study, and they must not be treated as confirmed identifications. Their importance is that they blur the boundary between a galaxy, a star cluster, a forming massive object, and a feeding black hole. The universe may not have built seeds in categories as neat as the names suggest. A source that looks like a young black hole may also contain intense star formation. A source that looks stellar may hide accretion. A source that points toward direct collapse may later be explained by rapid growth from a smaller seed. The dot becomes a crossroads. This is where the seed debate becomes less like sorting shells on a table and more like interpreting footprints in wet sand before the tide erases them. For the listener, the human-scale version is a distant window at night. Through it, there is a red glow. It could be a lamp behind a curtain. It could be a fire in a stove. It could be several small lights blurred into one. From outside, the color alone is not enough. You need the flicker, the heat, the sound, the shape of the room, and what else is nearby. Astronomers need the same kind of layered evidence spectra, host galaxy measurements, gas velocities, X-rays where possible, infrared colors and comparisons across many sources. One red dot can suggest. A population can begin to argue. The micro payoff is that little red dots are not answers disguised as points of light. They are test sites. They force seed models to face early objects that may be compact, active, gas-rich, and oddly balanced between black hole and galaxy. If many are young, accreting black holes, then the early universe formed and fed black holes efficiently. If only some are, then the population still helps separate black hole growth from extreme star formation. If their interpretations evolve, that evolution will sharpen the physics rather than weaken the mystery. The safest statement is also the most useful. Little red dots may contain some of the missing middle, but they do not yet reveal a single universal beginning. To move from suggestive dots to a real origin story, scientists need tests that can weigh the black hole, measure the host, trace the gas, and compare one early object against another. The next question is how those tests can distinguish a light seed grown fast from a heavy seed born large. A black hole seed cannot be tested by asking only whether a distant point is red, bright, or compact. Those clues begin the investigation, but they do not finish it. To distinguish a light seed that grew quickly from a heavy seed that began, large scientists need to reconstruct a history from fragments of light. They need to estimate the black hole's mass, the mass of the surrounding galaxy, the speed of accretion, the motion of gas, the chemical state of the system, and the number of similar objects that appear across cosmic time. Each measurement is uncertain on its own. Together they begin to form a pattern. This is the careful way the seed problem can move from possibility toward evidence. It is not enough to find one dramatic object and give it an origin. The question is whether many objects measured in many ways lean toward the same kind of beginning. At first, mass seems like the most direct test. If a black hole in the early universe appears too massive for a small seed to have grown under ordinary assumptions, then a heavy seed becomes attractive. If the mass is lower and the object looks like an intermediate step between stellar remnants and later giants, then a light seed with efficient growth may remain plausible. But black hole mass in the distant universe is not placed on a scale. It is inferred. Astronomers often use the brightness of accretion and the widths of spectral lines which can reveal how fast gas is moving near the central object. Faster gas can imply deeper gravity. Deeper gravity can imply more mass. But geometry matters, orientation matters, radiation matters. The gas may not move in a simple orderly pattern. The host galaxy is just as important. A black hole that is enormous compared with its young galaxy may suggest a different history from a black hole that grows in step with its stars. If the central object seems to have outrun the galaxy, scientists may ask whether it began as a heavy seed accreted rapidly or both. If many early black holes are found with more modest masses relative to their hosts, that may support a pathway where smaller seeds grow more gradually within assembling galaxies. But host galaxy mass is also difficult. Young stars can be bright in ways that make a galaxy seem heavier or lighter, depending on the model. Dust can hide some light and redden other light. An active nucleus can contaminate the starlight used to estimate the galaxy. Separating the black hole from its home is like trying to weigh a candle, and the room around it while both are seen through fog. Gas chemistry provides another clue. Heavy direct collapse scenarios often depend on primitive or special gas conditions, where cooling and fragmentation are controlled. If an early object is found in an environment with very low heavy element content, or with signatures suggesting intense radiation and unusual gas behavior, that may strengthen some heavy seed interpretations. But chemistry evolves quickly. The first stars can enrich nearby gas. Galaxy mergers can mix material. A black hole may be observed long after the conditions of its birth have changed. The gas we see may not be the gas that made the seed. This is why chemical evidence is useful but rarely decisive by itself. It can point toward an environment but not always preserve a birth certificate. Accretion rate is another test because it asks how hard the seed is currently feeding. A light seed model may require episodes of rapid accretion to explain some early massive objects. If astronomers observe black holes feeding near or above simple steady expectations, they gain evidence that fast growth is physically relevant. Yet a current accretion rate is only a snapshot. A black hole shining brightly today may have been quiet before. A quiet black hole today may have grown rapidly in the past. The growth history is a movie, but telescopes usually catch frames. Scientists therefore compare many frames from many objects at different distances and ages, trying to infer the rhythm of growth. The pattern matters more than one pose. Population statistics may be the strongest long-term test. Light seeds should be common if many massive early stars left remnants, but most may stay small or invisible. Heavy seeds may be rarer, but each begins with more mass. These pathways predict different numbers of observable growing black holes, different mass distributions and different relationships with host galaxies. If future surveys find a large population of lower mass early active black holes that may favor abundant light seeds plus varied growth, if they find many overmassive black holes in tiny early hosts that may increase pressure for heavy seeds or extreme accretion, if the population is broad and mixed, then the answer may be plural. The universe may not have chosen one seed recipe. Gravitational waves add a different kind of promise. Light from accretion tells us about gas around black holes. Gravitational waves tell us about black holes merging. Future detectors sensitive to massive black hole mergers could reveal whether early seeds combined, often what masses were involved, and how mergers contributed to growth. This would not replace telescopes, but it would add another sense. Seeing accretion is like seeing smoke from a hidden engine. Hearing gravitational waves would be like feeling the engine parts strike together. Together they could turn a silent origin problem into a multi-messenger history. The micro payoff is that seed models can be tested, but not with a single golden clue. Scientists need spectra to study gas infrared light to find early galaxies, X-rays to reveal hidden accretion, where possible simulations to connect physics across scales, and gravitational waves to trace mergers. Each method has blind spots, but each removes one layer of ambiguity. A light seed grown fast, a heavy seed born large, and a mixed pathway can sometimes look similar. They become harder to confuse when mass-host gas number counts and merger history are placed together. That is why the next stage of the mystery is not merely discovery, it is comparison. Once enough early black holes are measured, the division between light and heavy may begin to soften, because nature may have left not two neat boxes, but a continuum of dark beginnings. The division between light seeds and heavy seeds is useful, but it can become too neat. It makes the early universe sound like a field with two kinds of dark grains scattered into it, small remnants from the first massive stars on one side, large direct collapse objects on the other. For teaching the mystery, the division helps. It shows the central tension. A small beginning requires difficult growth. A large beginning requires difficult birth. But nature is not required to honor the boundaries of our categories. The more scientists study seed formation, the more the clean line begins to blur. A black hole seed may begin in one channel and then quickly be reshaped by another. A light seed may grow in a burst and become difficult to distinguish from a heavier seed later on. A heavy seed may pass through massive star-like stages rather than appearing as a simple jump into darkness. Mergers can combine beginnings that once belonged to different stories. The boxes are helpful. The universe may be less tidy. At first, the two-seed framework feels like a choice. Did the first supermassive black holes grow from small stellar remnants, or did some begin as heavy direct collapse seeds? But this question may be too narrow if it is asked as one answer for all galaxies. The early universe was not uniform. Some regions were denser than others, some halos assembled quickly, some were exposed to stronger radiation from nearby star-forming neighbors. Some gas clouds remained more pristine while others were enriched by earlier stars. Some environments supplied fuel steadily, while others delivered it in violent episodes. Under such varied conditions, it would be surprising if every successful black hole followed the same road. A population can contain more than one origin without becoming vague. The task is to learn which pathways mattered where they mattered, and how often. This is the hidden scientific turn. The seed problem is not only a question of identity, but a question of distribution. A single object can tempt a dramatic label. A population demands a map. If early black holes appear across a range of masses, host galaxies, accretion rates and environments, then the answer may be a spectrum rather than a switch. There may have been many light seeds, most of them faint or stalled. There may have been rarer heavy seeds, some important for the earliest massive systems. There may have been intermediate beginnings where unusual stellar clusters, runaway collisions, dense gas inflows, or massive star-like objects created black holes larger than ordinary stellar remnants, but not as massive as the boldest direct collapse scenarios. The familiar names remain, but their edges soften. A seed is not only light or heavy, it is placed somewhere on a landscape of starting masses and growth histories. For a human-scale image, imagine trying to classify rivers only as streams or great channels. The distinction is real, but it leaves out tributaries, floods and underground flows. A black hole seed is not a river, yet the image helps with the danger of oversimplification. A light seed in a rich environment may gain mass quickly and enter the middle range. A heavy seed in a poor environment may remain less impressive than expected. Two modest seeds may merge. A buried accretion episode may change the mass faster than the galaxy around it changes. By the time astronomers observe the object, the original label may be partly erased. The seed has already lived. This matters for interpreting Webb's early discoveries. A compact red source that appears to contain a large black hole does not automatically prove direct collapse. It may indicate a heavy seed, but it may also indicate rapid accretion from a lighter beginning and certain mass estimates, unusual stellar light, or a combination of effects. Likewise, a lower mass early active black hole does not automatically prove light seeds as the universal pathway. It may be one member of a wide family. The purpose of observation is not to force every object into a pre-selected box, but to let the population reveal which boxes are too small. The most honest models will have to handle overlap. They will have to allow that different black holes reach similar masses by different routes, and that similar seeds reach different endings because their galaxies treated them differently. The temptation is to want one origin story because one story is easier to remember. But the universe often builds important structures through many channels. Stars form across ranges of mass. Planets assemble in different disks and migrate through different histories. Galaxies grow through gas inflow star formation and mergers in different proportions. Black holes may be no different. A supermassive black hole at the center of a galaxy could be the final result of a light seed that fed efficiently, or a heavy seed that formed rarely, or a sequence of mergers and accretion episodes that makes the first label less visible. The ending can look similar even when the beginning was different. That is what makes the archaeology difficult. The fossil has been transformed by everything that happened after burial. The micro-payoff is that the seed debate becomes more powerful when it stops pretending that the answer must be singular. Light seeds and heavy seeds are not useless categories. They are anchor points. They define the extremes of a problem. Between and around them lies a wider space of possible origins shaped by gas physics, stellar evolution, galaxy assembly radiation, and time. This wider view does not weaken the central question. It sharpens it. Instead of asking which seed wins, everywhere scientists can ask which conditions produce which beginnings, and which beginnings grow into which observed populations. That is a difficult question, but also a realistic one. It fits the uneven early universe better than a single universal recipe. By this point, the giant black hole no longer looks like an object with one hidden answer beneath it. It looks like the visible tip of an ancestry tree whose branches may include stellar deaths, collapsing gas clouds, rapid feeding episodes, and mergers. To understand that ancestry, the next step is almost archaeological. Each early black hole becomes a relic of the conditions that made it, and each seed becomes a clue to what the young universe was able to build. A black hole seed is a clue to a world that no longer exists. The gas that made it has changed. The first stars that may have surrounded it are gone. The small galaxy that held it may have been swallowed into a larger one, and the light from its earliest growth has been stretched thin by the expansion of the universe. Yet something of that beginning remains in the objects astronomers search for now: a compact red source, a faint active nucleus, a black hole that seems heavy for its young host, a spectrum whose lines carry the motion of gas near a hidden center. These are not fossils in rock. They are fossils made of light. They do not preserve the shape of the seed directly. They preserve the consequences of a seed that survived long enough to change its surroundings. This is why the question of origins feels like archaeology, but archaeology performed across distance instead of soil. The excavation is not downward, it is backward. At first, black hole seeds seem like a narrow problem inside astrophysics. They belong to black holes, accretion disks, early galaxies, and the physics of collapse. But their meaning spreads outward. To know what kinds of seeds formed, scientists must know what the first stars were like, how quickly the earliest gas became enriched with heavier elements, how radiation from young galaxies changed nearby clouds, how dark matter halos gathered ordinary matter, and how the first small galaxies merged into larger structures. A seed is not an isolated dot. It is a record of conditions. If light seeds dominated, then the first massive stars and their remnants may have supplied the main population of black hole beginnings. If heavy seeds mattered strongly, then the early universe must have produced rare places where gas could avoid ordinary star formation and collapse in a more direct way. If both pathways occurred, then the seed population becomes a map of cosmic diversity. The smallest beginning points back to the largest environment. This is the quiet philosophical turn in the science, though it does not require anything vague or sentimental. A supermassive black hole is often imagined as an endpoint, a final concentration of gravity so extreme that nothing crossing its boundary can return. But in the seed problem, the black hole becomes a historical object. It is not only a sink, it is evidence. Its mass, its feeding rate, its host galaxy, and its place in cosmic time all ask what the universe was capable of building when it was young. The dark object becomes a kind of witness, not because it remembers in any conscious sense, but because physics leaves traces. A black hole that grew too early or seems too large for its host carries pressure from its past. It tells scientists that at least one route through birth fuel and time must have been open. The challenge is to find which route. Imagine standing before a vast ancient city after most of its earliest foundations have been rebuilt again and again. The stones now visible are not the first stones, but their placement may reveal where the first walls stood. Later, construction can hide the beginning, yet it cannot be completely independent of it. In a similar way, a modern or distant supermassive black hole has been transformed by accretion mergers, feedback and galaxy growth. But the starting mass still affects what was possible. A light seed must have crossed a longer road. A heavy seed must have been born in a rarer room. A mixed history must have carried signatures of both. The present object is not a perfect archive, but it is not empty of memory. The archive is damaged. That is why it matters. There is also humility in the seed question. It reminds us that seeing farther does not always mean seeing the answer directly. Webb can reveal early galaxies and compact sources with extraordinary sensitivity, but it still sees light after the fact. A spectrum can suggest accretion. A color can suggest dust or distance. A line width can suggest motion near a black hole. A mass estimate can suggest an origin pathway, but suggestion is not birth witnessed in real time. The first seed itself may remain hidden behind the opacity, faintness, and complexity of cosmic dawn. Science moves anyway, not by pretending the hidden thing has been seen, but by building constraints around it. If the seed cannot be observed directly, its absence becomes a shape outlined by evidence. That is a different kind of seeing. The micro-payoff is that black hole seeds are not only beginnings of black holes, they are probes of the early universe's rules. They ask how gas behaved before galaxies became mature, how the first stars ended, how radiation changed collapse, how quickly structures merged, and how efficiently gravity could concentrate matter in the first cosmic neighborhoods. In that sense, the seed is small only in the story's starting frame. Its implications are large. A single dark beginning can connect stellar death gas chemistry, cosmic structure, and the first active galaxies. This is why no responsible answer should flatten the mystery into one slogan. The universe may have built giants from small remnants in some places and from heavy beginnings in others. It may have allowed rare direct collapse events, common stellar remnants, rapid bursts of feeding and long chains of mergers. The origin problem is not weaker because it is plural. It is richer because it follows the unevenness of the real universe. By now the original giant black hole has changed in meaning. It is no longer merely an enormous gravitational well at the center of a galaxy. It is the visible end of an ancestry that reaches back into primordial clouds, massive early stars and galaxies still forming their first shapes. To finish the journey, the story has to return to that giant and see it with the seed restored beneath it. The last question is not whether one model can win in a simple way. It is what we can honestly say when all the clues are placed together: the dark seed, the feeding light, the merging galaxies, and the young universe that made room for them all. The giant black hole now looks different from the one at the beginning. It is still vast, still dark at its boundary, still able to gather gas into brilliance and bend the motion of stars around an unseen center. But it no longer feels like an isolated monster that simply appeared inside a galaxy. It feels like the final visible shape of a question that began much earlier when the universe was younger, poorer in heavy elements, richer in unsettled gas, and still learning how to build its first structures. Rewind the giant far enough and the bright disk fades again. The host galaxy becomes smaller. The surrounding stars become fewer and more primitive. The familiar categories of mature cosmic architecture fall away. At the deepest layer, the black hole becomes not a giant but a beginning, a seed. And that seed remains one of the missing first pages in the story of cosmic growth. The safest answer is not the loudest one. Scientists cannot yet say that all supermassive black holes came from one kind of seed. They cannot say that direct collapse has been directly observed in its first moment. They cannot say that primordial black holes are confirmed as the solution. They cannot turn a compact red source into a birth certificate. What the evidence allows is more careful and more interesting. Some black hole seeds may have been light-born from the collapse of massive early stars. These beginnings are natural because stars can die into black holes, and the first generations of stars may have produced remnants capable of becoming the first dark points. But a light seed begins far from supermassive scale. It needs fuel, time, and favorable conditions. It may need rapid episodes of accretion repeated feeding mergers or an unusually supportive host galaxy to reach the masses seen in some early systems. Smallness is not failure. It is a demand placed on everything that follows. Other seeds may have been heavy formed when large primordial gas clouds collapsed under special conditions, rather than fragmenting into ordinary stars. This pathway gives the black hole a head start, but it asks the early universe for something rare. The gas must stay coherent enough. Cooling and fragmentation must be controlled. Radiation turbulence, rotation and inflow must align in a way that allows a massive central collapse. A heavy seed solves part of the clock problem by beginning closer to the finish, but it creates a different question about how often such special nurseries existed. The origin is easier to grow, but harder to arrange. That is the balance that returns again and again. Every answer moves the difficulty to another layer. Rapid accretion can help smaller seeds grow quickly, but it requires dense inflows, favorable geometry, and enough time spent in intense feeding phases. Mergers can add mass and combine separate beginnings, but black holes must first find one another, sync together and merge efficiently inside young galaxies. Webb's early observations can reveal compact sources, active nuclei and red objects that may hold clues to the missing middle, but the light arrives blended with stars, dust, gas and distance. The evidence is not empty, it is layered. Each layer improves the map while reminding us how much of the route is still hidden. This is why the seed problem is not a failure of imagination. It is a test of beginnings. A supermassive black hole asks for a sequence that can actually happen: formation, survival, fuel, delivery, feedback, possible merger, and continued growth. Remove any one part and the path can fail. A seed may be born but never fed. It may be fed but then blown clear of fuel. It may merge but lose its place at the center. It may shine so brightly that its own radiation reshapes the flow around it. The giant that survives is therefore not merely massive, it is successful. It is the descendant of a beginning that found a route through a dangerous early universe. For a human-scale image, think of an ancient tree whose trunk is enormous, but whose first sprout was never seen. The rings may tell of droughts, fires, and long seasons of growth, but the exact moment of germination is gone. A black hole has no rings that can be cut and counted. Its archive is stranger spectra, host galaxies, gas motions, red-shifted light number counts, and the faint signatures of accretion. The first sprout is missing, but the later structure still carries constraints. It cannot have grown from just anything, anywhere, at any pace. Physics narrows the possible past. Observation narrows it further. The final synthesis is therefore plural but not vague. The universe may have built some giants from small stellar remnants that grew with extraordinary efficiency. It may have given others a massive head start through direct collapse. It may have blended pathways, allowing seeds of different masses to accrete, merge, stall, revive or hide. No single pathway has been proven for all supermassive black holes, and that uncertainty is not a weakness in the story. It is the shape of the real frontier. The first black hole seeds sit at the meeting point of stellar death. Gas collapse, galaxy assembly, radiation feedback, and cosmic time. To understand them is to understand how the young universe first made gravity irreversible on the road to becoming enormous. The giant at the center is still the object we can name, but beneath it is a smaller, darker question. Was its first self a remnant of a dead primordial star, a heavy collapse from a rare cloud, or the beginning of a more tangled ancestry that no single label can hold? The answer has not been fully recovered, but the search has changed the way the giant is seen. It is no longer only an endpoint. It is evidence that somewhere in the early dark, the universe found a way to plant gravity deep enough that time gas and merging galaxies could grow it into one of the largest hidden structures we know. In the end, the seed remains hidden, but it is no longer empty. It has become the small dark space where many parts of the early universe meet. A first massive star dying in a young galaxy. a vast gas cloud refusing to fragment, a black hole feeding through thick, unstable flows. Two dark objects spiraling together after their galaxies have merged. A compact red point in Webb's deep vision, not yet a final answer, but a pressure mark against every simple story. The beginning of a supermassive black hole is not one moment easily recovered. It is a chain of conditions, and each link has to hold. That is what makes the mystery quiet and powerful. The universe did not merely place giants at the centers of galaxies. It had to make beginnings capable of becoming giants. Some beginnings may have been small and patient. Some may have been heavy and rare. Some may have grown in sudden hidden bursts or merged through the long assembly of cosmic structure. The answer may not be one seed, but a family of origins, each shaped by gaslight, gravity, and time. And so the giant black hole changes in the mind. It is still dark, it is still immense, but it is also a trace of something more fragile, a first collapse that survived. Somewhere in the young universe, matter crossed a boundary and became a seed. Around it, galaxies formed, stars burned, gas fell, radiation pushed back, and time widened the distance between the beginning and the object we can observe. The first page is missing, but the search for it has already revealed something profound. Even the largest darkness in the universe may depend on the smallest beginning.